You know about this. Regarding early birds, so far I've received one note and one note only. I told you if you did this on an early bird basis for exam 1, I still need a note. Because I'm not going to know about you by osmosis. For early birds, if possible, I want you to start at noon or 1 or 2 or 3 or at 1, 2, noon, 1, 2, or 3 p.m. So I don't have to go up there at 2:10 and 12:15 and 3:05 and stuff like that. I'm just not that flexible. Now then, to make sure everybody receives the same treatment regarding yesterday's discussion class considerations. The last stuff involved conversion considerations for semi-soluble salts, whose chemistry we considered in chapter 19 earlier on, whose chemistry you've considered by way of work in laboratory, 46L. How do I take this semi-soluble salt and, if possible, turn it into a different semi-soluble salt? Like calcium carbonate and the calcium sulfate. I've offered you 4 choices. Obviously, you need a sulfate source. Sodium sulfate solution, ammonium sulfate solution, sodium hydrogen sulfate solution, sulfuric acid solution. To turn calcium carbonate into calcium sulfate, what relative properties of these two materials need you consider? What? Solubility. Which one in the presence of water is more stable? Which one of these two salts of calcium ion is less soluble, more stable in the presence of water? Which one? We've done this in class, and you've also done it in the lab for those of you in 46L. Which one? Calcium carbonate is more stable. So the fight you have on your hands here is twofold. One, you got to provide a sulfite source, but that's not enough, because calcium carbonate is more stable than calcium sulfate, which means if you take a solution in which you have both carbonate ion and sulfate ion present at equal molarities, and you put in calcium ion, which of these materials are you going to form preferentially? Calcium carbonate. So if you just supply sulfate, you'll convert some calcium carbonate to calcium sulfate, but the conversion effectiveness will be pretty poor. That rules out choice 1. How would you calculate K for this first choice? If you write calcium carbonate plus sulfate ion in equilibrium with calcium sulfate plus carbonate ion, what's K? Calcium carbonate plus sulfate ion in equilibrium with calcium sulfate plus carbonate ion. What's K for that?
Very small.
How do I get the K? What are the fundamental Ks of which this equilibrium reaction is composed? You want to see this now in your mind's eye. Calcium carbonate plus sulfate ion. Double arrows, calcium sulfate plus carbonate ion. Does this equilibrium not scream at you that it's composed of the two semi-soluble salts, calcium carbonate as a reactant and calcium sulfate as a product? So you need KSP for these salts. Is KSP calcium carbonate numerator or denominator? Numerator. Calcium sulfate KSP. Numerator, denominator? Denominator. So there you have it. 6.2 times 10 to the minus 9 divided by 9.1 times 10 to the minus 6. And since you got 10 to the minus 6 divided by 10 to the minus 9, Pardon me, 10 to the minus 9 divided by 10 to the minus 6, let me say this right, without even paying attention to the significant figures, 10 to the minus 9 divided by 10 to the minus 6, you know this is a K value a lot smaller than 1. That means an ineffective conversion. Have you by now had it sink in that if you got a K value of 1, the conversion effectiveness is 50%? So if you got a K value a lot smaller than 1, the conversion effectiveness is a hell of a lot smaller than 50%. All right, ammonium sulfate. Is that a better method? Because again, the fight you have on your hands here is twofold. Calcium carbonate is more stable, less soluble in water than calcium sulfate. So beside providing a sulfate source, what else do you have to do to bring about this conversion? What else? What else do you have to do? You got to murder carbonate ion. Is carbonate ion much more readily murderable than sulfate ion? Which of these bases is far more easily murdered? Which one? Carbonate, because it is a much stronger base, you betcha. You can't separate acid-base chemistry from this stuff. Again, that's why we did chapter 18 before we did chapter 19. Because damn near everything that happens in water solution depends on acid-base chemistry somehow. It's very important. Arguably, Bronsted-Lowry acid-base chemistry is the most important chemistry in water solution. So when we look at this second choice, we got ammonium ion to go after carbonate ion, and sulfate ion to go after calcium ion. But we've already looked at the equilibrium calcium carbonate in the presence of ammonium ion, right? Because we considered the solubility of calcium carbonate in 1 molar ammonium chloride solution. Was calcium carbonate particularly soluble in 1 molar ammonium chloride solution? Did we find that to be the case? Yes or no? No. So this second attack is still not particularly effective. Because although ammonium ion protonates carbonate ion, it converts it in the main to bicarb ion, which means you still got carbonate in the system. A form of carbonate is still in the system. Now let's look at choice 3. Hydrogen sulfate ion. When H plus is stripped from hydrogen sulfate ion, you got your sulfate ion. Will a combination of hydrogen sulfate ion with calcium carbonate result in stripping H plus from hydrogen sulfate ion? Put another way, how effective is the reaction? Hydrogen sulfate ion plus carbonate ion. If I treat carbonate ion with hydrogen sulfate ion, may I expect to see bubbles? Well, I expect to see bubbles all over the place. Copious bubbling. Because hydrogen sulfate ion is a much stronger acid than H2CO3, which ammonium ion is not. So guess what? If I hit carbonate ion or calcium carbonate with an acid that's stronger than H2CO3, then I'm going to convert carbonate to H2CO3 effectively. And that readily leaves the system, doesn't it? Because H2CO3 isn't very stable, isn't it? Is it? So out bubbles CO2. And now I got carbonate ion killed quite effectively. Point, if you write the correct reaction equation for calcium carbonate plus hydrogen sulfate ion, and calculate K, you're going to get a damn big number. Because that conversion works like a shot. Now let's look at the last choice. Sulfuric acid. How will the effectiveness of sulfuric acid compare to the effectiveness of sodium hydrogen sulfate solution in converting calcium carbonate to calcium sulfate? Is the sulfuric acid solution less effective or more effective? More effective. Because you still got hydrogen sulfate ion in there, don't you? But now you got even a better acid to attack carbonate ion, don't you? You got hydronium ion. The Ks for each of these attacks are very huge, but for sulfuric acid attack, it's more huge, or huger, if you like. All right, 1930-31. We talked previously about reactions involving silver chloride and ammonia. And recognize, when ammonia successfully dissolves silver chloride, you make the silver ammonia complex ion. But from a who makes a stronger bond standpoint, or which is a stronger Lewis base towards silver ion, we found out that chloride ion wins. So we're able to get silver chloride to dissolve in the presence of ammonia by the gang-up factor. Now let's subject silver oxide to similar consideration. Well, before we talk about converting silver oxide to the silver ammonia complex ion, given that we know silver chloride is more stable than the silver ammonia complex ion, what would happen to silver oxide if you subject it to treatment with chloride ion? Would silver oxide readily convert to silver chloride? If you say yes, then you're telling me silver chloride is a good deal more stable than silver oxide. Do you believe that's true? Look at your information sheet. What I want, or what I hope to achieve with my directive now of you being asked to look at your information sheet, is to debug something. We reminded you previously, you may not immediately assess the solubility of a salt based on its KSP relative to another salt, unless the two salts have the same stoichiometry and the same kind of chemistry. You think there's a big difference in the chemistry between silver oxide and silver chloride? Well, stoichiometrically they're different, aren't they? 2 moles silver ion per mole of oxide ion, whereas 1 mole silver ion per mole of chloride ion. What else is a big difference between the chemistry of these two materials? Silver oxide versus silver chloride. Final exam question, Chemistry 2046. Your response to this question can earn you anywhere from plus 100 to minus 100. Question is, discuss the main differences in the chemistry between silver oxide and silver chloride. We've already looked at one, the stoichiometric difference. That's really a compositional difference more so than a chemical difference. Now let's talk about a chemical difference, a big chemical difference. I'm listening. If I hit silver chloride with hydronium ion, does silver chloride give a damn? Hell no! How about if I hit silver oxide with hydronium ion? Hey! Oxide ion says, ah, you're killing me! And away goes the silver oxide. So one is quite a basic salt of silver ion, isn't it? Whereas the other one is not a basic salt of silver ion at all. Even though chloride ion is, of course, theoretically a Bronsted base, because it's a negative ion. But in water solution, chloride ion doesn't even get in the game. So I ask the question again. If I treat silver oxide with chloride ion, do you think the silver oxide will remain intact, or do you think it will readily convert to silver chloride?
Is it why?
Now, if you look at the KSP information, which is on the information sheet, and see that the value for silver oxide KSP is on the order of 10 to minus 16, is that correct? Whereas for silver chloride 10 to minus 10, you may make the flatly wrong conclusion that silver oxide is more stable. because these materials are quite different stoichiometrically as well as chemically. So let's write the equilibrium reaction in our mind's eye. Here we go. Silver oxide plus, how many moles of chloride ion? 2. Silver oxide plus 2 moles chloride ion. Double arrows, 2 moles silver chloride. And what? Or did we leave something out as a reactant? Water. Need water, don't we, to get together with oxide ion. So beside silver chloride as a product, we got hydroxide ion, don't we? So what are you going to find is the K value, the equilibrium constant for this reaction? You're going to find KSP silver oxide in the numerator divided by what? I'm listening. Per mole of silver oxide converted, how many moles of silver chloride are we making? 2. So what are you going to find in the denominator? You got silver oxide KSP numerator. What you got in the denominator? KSP silver chloride squared. Ha ha! So it's 10 to the minus 16 divided by 10 to the minus 20. That's 10 to the 4th. This is a go, because silver chloride is a hell of a lot more stable and less soluble than silver oxide. As I told you, be careful. The KSP values themselves will lie to you, especially if you don't pay attention to the chemistry. Then they'll really lie to you. Upshot. Although you've not yet realized it. These materials are very similar in the thermodynamic stabilities. But silver chloride's a hell of a lot more stable than either one of these. Okay? Now let's talk about taking this and turning it into this. We got 4 possibilities. Because if I'm going to turn this into this, what chemistry do I have to bring about? Well, can we say flatly for starters, we got to supply ammonia. Can't make the silver ammonia complex ion if you don't supply ammonia. Fair enough? What else do we have to do? I'll give you a clue. This idea of this is just like the idea of calcium carbonate going to calcium sulfate. You had to supply sulfate ion, but you also had to murder carbonate ion, didn't you? So what do you got to do here? Besides supplying ammonia, you got to murder oxide ion if you want this conversion to be effective. This, folks, is the hard part of chemistry. Really. It's the hardest for anybody to learn how to understand reaction equations and listen to what they have to tell you. But if I can send you away from here with the knowledge and ability of doing this, you will have a lot of power before you in future chemistry studies. This gives me the ammonia, but it doesn't attack oxide ion. Now water will, because this is in water solution. This will give me ammonium ion. And ammonium ion attacks oxide ion. And when ammonium ion attacks oxide ion, do I make ammonia? When ammonium ion attacks oxide ion, do I make ammonia? Yeah. So this will give me ammonium ion initially, plus some ammonia along the way. How about this? Will this attack the oxide ion? Sure, this attacks the oxide ion. Ha ha! Well, what's this going to do? You're going to make this? Hell no! Now you make silver chloride. We'll throw this one away. That's just a bug I put in there. I always want to see if you're thinking. Students say, oh, that's a dirty question. Hey, thinking is where it's at. Period. Now let's look at this system. How do you think the effectiveness of this system compares to either of these? Because in this system, not only are we starting with ammonium ion at a high concentration, so we will effectively bop oxide ion, we also have initially ammonia at high concentration. So after bopping oxide ion, which sets silver ion free from the silver oxide lattice, I've got the ammonia molecules there and ready to glom on the silver ion and make the silver ammonia complex ion. So this is by far the best. Now let's have a little fun. On your paper right now, I want you to follow this directive. Reaction equation, silver oxide and ammonium ion. Let's go right now, quick. And let me direct you in this fashion while you're writing this equation. By treating silver oxide with ammonium ion, can you or can you not convert all the silver ion to the silver ammonia complex ion? That's the question. In treating silver oxide with ammonium ion, can you or can you not convert all the silver ion to the silver ammonia complex ion? You keep that in mind as you write this equation. You think you might have to write some equations tomorrow to answer some of these questions? If you can't, don't even bother to show up. Well, show up, but be prepared to take a beating. I don't want that. I want you to show up, but I want you to beat the exam, not the exam beat you. We got it? Time's up. Let's put this up here. So no limitation on moles of ammonium ion available. Excess ammonium ion. Little bit of that, a lot of that. Okay? We know that when ammonium ion attacks oxide ion, we will make ammonia. What will we make beside ammonia? We will not. You're not making hydroxide ion in the presence of excess ammonium ion. You'll make water. Right? Ammonium ion, hydroxide ion is a large extent reaction. You're not making any hydroxide ions in the presence of ammonium ion. You don't make strong bases in the presence of acid. Hey. Statement. If as yet you haven't realized such, if you believe that treating this with this gives these two as products and nothing else, you'll never be able to write an equation. Why not? To kill this in excess ammonium ion, per mole of this, how many moles of ammonium ion are required? How many? 2. In your mind's eye, you see the reaction equation. 2 moles ammonium ion, 1 mole oxide ion, products, 2 moles ammonia, 1 mole water. Done. All the oxide ion's gone. So we wrecked all the oxide ion. And in so doing, how many moles of silver ion did we put in solution? 2. Now by the 2 moles of ammonium ion transferring H+, how many moles of ammonia have I made? 2. But I got 2 moles of silver ion in the system, don't I? If I want to complex all the moles of silver ion, how many total moles of ammonia do I need? 4. But I only got 2. So guess what? By this reaction and this reaction alone, I cannot possibly complex all the silver ion. I cannot convert all the silver ion contributed to the system to silver ammonia complex ion. So what's the remaining product? What is it? What is it? I'm listening. Looks like we have a problem. I hear a few mumbles, and the mumbles in most cases don't agree with the other mumbles. It's a mumble battle. I heard silver hydroxide. How about that? Silver ion. And now I can write an equation. Because now I recognize what all the products are. Does this look like an equation? Does this look like an equation? What I'm asking you is this a balanced statement? If it's a balanced statement, it's an equation. Does it show material balance? Does this statement show material balance? Does this statement show charge balance? Does this statement show charge balance? Yes or no? Yes. I hear a lot of no's. I'm looking at 2 moles left and 2 moles right. That shows charge balance to me. What's the matter? Did I mess you up by putting silver ion at the end? That's terrible. Really terrible. You're damn right this is an equation. And so, we now take a further look at the last general topic considered in chapter 19, which is more on writing equations for reactions, which is the toughest task that you folks will ever face in chemistry class. Because now you got to have knowledge of reactants, and then you got to have the ability to figure out what the products are if they're not told to you. And oftentimes this is tough. But if you always pay attention to a particular aspect of a chemical system, you always have the chance to win. To what aspect of the system do I refer? PSI! Yes, indeed. Then you can win. The one part of chemistry which is ever so important that I have not yet seen one general chemistry text ever tackle. They're scared of it. Because it's hard. I just want to get this text of mine written. I'm lucky if I can get a paragraph or 2 written a day. It's hard. But it'll get there. All right. Some systems. Cuprate ion. Now, if the cuprate ion exists, you see the formula here? If this ion exists, what do you think about the pH of the system? Let this thing talk to you. You've got a solution which contains this ion. My question to you is, from this formula and this formula only, if I tell you this ion is present and stable in the solution, what do you think about the pH of the solution? High, low, neutral? Quite high? Hey, see this? This thing is full of hydroxide ions in its composition. You got to have a system that's rich in hydroxide ion. pH is quite high. You're going to hit this with H2S. Now, in the chem notes, we are telling you that rather like silver sulfide, copper sulfide is a damn stable material of copper ion. Far more stable than that ion, far more stable than the copper ammonia complex ion, whose chemistry we'll talk about when we get to electrochemistry. Far more stable than copper oxide, whose chemistry you'll study in assignment 6 and 46L, and which we'll discuss in class. Copper sulfide's damn stable stuff. So if I put H2S in this system, which is quite basic, you think I will be providing a good source of sulfide ion? Because hydroxide ion will effectively deprotonate this thing, don't you think? And if copper sulfide is a hell of a lot more stable than this, what do you think the principal product is of this reaction? Copper sulfide. Boom. You can now write the reaction equation. Calcium hydroxide, treated with ammonium ion and bicarb ion. What do you think the principal product is for this reaction? Or products? Look at the system inventory. Quite a basic salt. And you have recognized that if I forget this part, this reacts with this quite effectively, yes or no? This reacts with this quite effectively, yes or no? Yes. And now, I'm going to have a system which is what? Acidic or basic? Basic. Okay? Because when this gets together with this, I'm making ammonia. And this is a source of what? Source of what? Carbonate ion. You think I might get calcium carbonate? You betcha. And this. If you calculate K for this thing, because you looked at K for calcium hydroxide plus ammonium ion. Big K. If you put the bicarb ion in there, do you think the K will even get bigger yet? Because now rather than have calcium ion in solution, you will precipitate calcium ion as calcium carbonate. And that stuff is damn stable. K for this reaction is really big. All right? Calcium carbonate plus water. I prepared this equilibrium by just taking some deionized water and shaking up some chalk in it. We'll pulverize the chalk first to make establishment of equilibrium take place more expeditiously. I'm going to take this saturated calcium carbonate solution and imagine treating it with 1 molar ammonium sulfate solution. If I do this, what will be the main reaction? The main reaction. Question. You see this system? If I say that I will prepare this system by taking a liter of deionized water, a liter, and I'm going to pulverize 1 mole of calcium carbonate, okay? I'm going to pulverize 1 mole of calcium carbonate. I'm taking 1 liter deionized water and 1 mole of powdered calcium carbonate and shake them together. Are we understanding now the system? Okay. What is the main component of that system beside solvent water? What is it? Calcium carbonate, isn't it? Because damn little of the calcium carbonate dissolved. 1.4 times 10 to minus 4 moles per liter is the solubility. So you got a whole lot of calcium carbonate in that system, but relatively speaking, not much calcium ion or bicarb ion or hydroxide ion. So, if I treat that system with 1 molar ammonium sulfate solution, what do you think would be the main reaction? Ammonium ion plus hydroxide ion? Ammonium ion plus bicarb ion? Sulfate ion plus calcium ion? Or how about ammonium ion plus sulfate ion with calcium carbonate? Isn't that the main component of the system that we prepared initially? Yeah. Now, do you think that treating calcium carbonate with ammonium ion and sulfate ion is an effective way to produce calcium sulfate? What would you do to find out? calcium carbonate plus ammonium ion plus sulfate ion, products, calcium sulfate, ammonia, and bicarb ion. Calcium carbonate plus ammonium ion plus sulfate ion, double arrows, calcium sulfate, ammonia, bicarb ion. What will you do to find out if that reaction effectively converts calcium carbonate to calcium sulfate? What will you do? Find K. How about that? And if you wanted, you can even calculate the solubility of calcium carbonate in the ammonium sulfate solution. Not really a solubility, because you're converting it to a different solid. So you're going to calculate really the effectiveness of that conversion. And you will find out it's not very effective. But it has a K value that's a lot larger than calcium carbonate plus ammonium ion alone. That system we've looked at. Because when you add sulfate ion, you put another pull on the calcium carbonate. The pull is to convert calcium ion in calcium carbonate to calcium sulfate, as opposed to just putting calcium ion in solution. D and E we've done. That's the ammonium, the silver oxide and ammonium ion stuff. F. Treat E with hydrogen sulfide solution. This is simple. We're going back to this. We've recognized that if I take this and treat it with this and this, then all the silver ion is complexable, because I got both ammonia and ammonium ion going for me. So 2 moles of silver ion here, which means 2 moles of silver ammonia complex ion producible. And when ammonium ion gets together with oxide ion, I'll make ammonia and water. You write the equation if you want to. The question is, after realizing that this stuff, by this treatment, the double attack treatment, the ammonium ion which clobbers oxide ion and the ammonia which grabs silver ion, effectively converts this to silver ammonia complex ion, which means if you were to calculate K for each of these, well, not this one, but for the ammonia attack alone, the ammonium ion attack alone, or the double attack of ammonium ion plus ammonia, you're going to get a big K value for this. Small K value here, small K value here, big K value for this. But now after creating all this silver ammonia complex ion, I'm going to treat this system with hydrogen sulfide, H2S. What do you think will happen? What do you think will happen? What will happen? Do you remember earlier on in chapter 19 when we were talking to you about learning how to take an equilibrium system for which you don't know the value for the equilibrium constant, and take the equilibrium system apart to realize what fundamental K's of which it is composed, and then you can calculate the K value? That a system we looked at was AgCl, silver chloride, which is damn stable. Much more stable than silver ammonia complex ion, much more stable than silver oxide. And treat the silver chloride with H2S. There's H2S. What did we find out? Silver chloride plus H2S. Anybody remember what we found out? Silver chloride plus H2S resulted in a reaction in which Ag2S was the silver-containing product and had a K value on the order of 10 to the 5th. What's that tell you? Which is far more stable, silver chloride or silver sulfide? Silver sulfide. So if silver chloride is known to be much more stable than the silver ammonia complex ion, and I hit silver ammonia complex ion with H2S, what do you think I'm going to wind up with? Silver sulfide. And quite effectively, because this system is acidic or basic. It's basic, isn't it? Hey, that makes H2S attack even more effective, because in this basic system, the H2S will readily convert to HS minus. Do you recognize from a very, very simple thermodynamic standpoint why this is a far better source of sulfide ion than this? What's the very fundamental simple thermodynamic standpoint? Why is this a much better sulfide ion source than this? Huh?
The H2S has to become that.
Why is this a much better sulfide ion source than this? One less proton. What's that mean? How about these structures? If I want to turn this into sulfide ion, how many HS bonds do I have to break? If I want to turn this into sulfide ion, how many HS bonds do I have to break? Which costs you more? Breaking 2 bonds the same way or breaking 1 bond? How about that? Hey, believe me, if you go to the candy store and you want to buy 2 pounds of licorice, that costs you twice as much as buying 1 pound of licorice, doesn't it? Same idea here, isn't it? Have fun tomorrow. Chapter 20.